Hello, my name is Fritz Seveski. I'm a research engineer working at the Solar Thermal Energy Department at CENER in Spain. Today I'm going to present the Mosaic project. Mosaic means Modular High Concentration Solar Configuration. And the project has been financed by the European Commission within the Horizon 2020 framework. First of all, I'm going to start with the contents. I'm going to explain the Mosaic project concept. I'm going to explain the solar field concept, then the module's assembly process, then the receiver, the tracking system, and finally the prototype construction and the conclusions. The project concept is about a spherical concentrator where the concentrator is fixed and the absorber is moving. Okay? As commonly known, a sphere concentrates the incoming radiation on a line which goes through the center, and the focal spot is within the 1/2 of the radius, okay, as you can see here in the figure. And the basic motivation is to achieve high concentration ratios with comparable lower investment. So we would be in the order of magnitude of parabolic troughs or linear Fresnel regarding the investment, but with the efficiency we would be in the order of magnitude of power tower central receiver plants. Okay. On the right hand side you can see the view of the Mosaic prototype. Of course the system is modular, so we would, in a commercial unit, we would install several of such spherical concentrators where the receivers are moving for each concentrator, and then we would connect the modules with the heat transfer fluid circuit. The heat transfer fluid would be molten salt in a commercial unit. The prototype itself is operated with thermal oil because it's simpler and there is no risk of freezing. The goal is, of course, to achieve a very low LCOE in order to make the CSP technology competitive with other renewable energy technologies. When we think about the spherical concentrator, it is important to note that there are several ways to accomplish a spherical concentrator. Of course, we could implement an actual sphere where we would construct a large sphere with mirrors, and then this sphere would concentrate radiation on the center line according to the principle explained before. An additional approach would be a Fresnel sphere concept where we implement Fresnel lenses on a plane. Okay. The advantage of the first two approaches, the disadvantage of the first two approaches are that the concept requires a quite large area of installation, a high amount of civil works, as the sphere is not easy to construct, and in the case of the Fresnel, on the planar Fresnel configuration, we need a high land area. So the two first approaches are not recommended. But the last one, the semi-Fresnel approach, is the best choice, where several fractions of a sphere with same center but different radius are placed concentrically. And in this way you can achieve a quite optimum configuration with respect to size, okay, because size is important. We need to keep it small in order to reduce costs. Here you can see the conceptual design of the concentrator design of a prototype, of the Mosaic prototype. The prototype has an approximate size of 600 square meters of mirror aperture, and for example the ring dimensions are about 15 meters radius for the first ring, 16 meters radius for the second, and the third radius has about 18 meters. Okay, this configuration has been optimized for a latitude of 42.59 degrees north. Of course, if the system is installed in a different location, the configuration has to be optimized for the specific latitude. Okay. The next slide shows the design of the Mosaic prototype. As you have seen before in the previous slide, we could implement a continuous reflecting ring, but in practice it is easier to implement a modular approach where each ring is composed of small mirrors, which can be standardized in some sense, and then the implementation is more cost effective. So in our case, we used mirrors of 1 square meter of aperture each, and we assembled those mirrors in order to reproduce the 3 rings I presented in the previous slide. For example, the center sphere would consist of modules where we place 5 times 5 mirrors, and the outer concentrators would be represented by 3 times 3 mirrors. Okay, of course this depends on the specific design, but this was a solution for the Mosaic project. Of course, the system needs to be designed such that it withstands strong winds. We designed the system such that it withstands 100 kilometers per hour maximum wind speed according to the technical building code in Spain, and the service limit state is about 30 kilometers per hour maximum wind speed. You can see here some pictures of the CFD simulation, and you can also see a picture of the structure of the mirror module. Okay, on the lower right side. Of course, we also need to mount the reflective mirrors on the structure, and this has to happen in a very accurate way in order to optimize the optical efficiency. And in order to achieve this in a very accurate manner, we had to construct a master structure where the mirrors are placed and then fixed to the supporting structure. So the master structure defines the shape of the mirrors and the exact position, and then once the exact position is defined, we can fix the mirrors on the supporting structure. Of course, then afterwards we did check if the accuracy is acceptable, and we did this accuracy check with a laser, and we measured the deviation, the optical deviation of each mirror and each mirror module, and we were lucky, and the mounting process worked as expected. Next, the solar receiver design. The solar receiver design is quite cumbersome and not easy, because the incident flux varies a lot. It varies not only throughout the year, it also varies throughout the day as a function of solar position. And here you can see the simulated solar flux during one day, starting at 8 o'clock in the morning at sunrise and lasting until the afternoon. So this square shape you can see here is the surface of a cylinder rolled out, and well, the cylinder is shown on the left hand side, and if you consider only the surface of the cylinder, you obtain the following graphic. In color we see the flux in watts per square meter, and the picture is moving starting at 8 o'clock in the morning with the flux corresponding to 8 o'clock in the morning, and moving throughout the day. as you can see, the flux shape moves a lot, and depends also, well, depends on the hour and on the, of course, on the date. So in winter the shape would be different than in summer, which means that the solar receiver must cope with a highly variable solar irradiance. And here we have to think about how we can best design a solar receiver in order to have high thermal efficiency throughout the year. We started with an annular configuration where the solar receiver is a cylinder, tubular configuration where we have two concentric cylinders, and the heat transfer fluid flows in the annular space between two tubes. This configuration has shown to have problems because we have first laminar flow, bad heat transfer, and also the outlet temperature cannot be reached because thermal losses are high, and the flux distribution is not suitable for this type of receiver. Then we moved to the same concept, but with three sections, with three annular sections. You can see here down on the picture. You can see here the space is divided into three annular sections. This concept has shown the same performance, the same bad performance. So we cannot achieve the temperature set point because we have laminar flow, bad heat transfer, and relatively high heat losses. Then we moved to external tube configuration, where we put small external tubes around the receiver. In this case worked well because we have turbulent flow, but we found that the optimum configuration would be a helical configuration, where a tube is wound around the receiver tube in a helical configuration. Okay, and in this way we achieve the best thermal performance, and we can capture the maximum energy delivered to the receiver. Here you can see the prototype in the manufacturing process. You can see here the cylindrical receiver shape and the helical absorber tubes installed around the central receiver structure. And on the right hand side you can see the picture of the manufactured receiver ready for delivery to the plant. At the moment the construction is ongoing, and here you can see a scheme of the tracking system. Well, the idea is to pull the receiver with cables in the space available in order to best track the sun during the day and during the season. And we would need 4 masts installed around the mirror in order to be able to track the solar receiver according to the movement of the sun. You can see here the different components. You can see the cable support, the towers needed for the support of the cables. Then you can see here the central tower where the heat transfer fluid is guided to the receiver with a flexible hose. And of course you can see the receiver which is fixed to the cable system and which is moved throughout the focal space, focal area defined by the mirror design. The prototype is currently being constructed in the north of Spain, at the installations of Tener, and at the moment we have installed the towers, the 4 towers for the cable tracking. Then we have installed the central tower with the thermal loop where the HDF flow will be simulated with with a HDF vessel, then a pump, and a refrigeration system where we cool down the oil after being heated up in the solar receiver. You can also see here the control room from where we are going to control the experimental plant. And this is the current state of the prototype. It is expected that the operations, well, the construction work will finish at the beginning of 2021, and then the experimental evaluation is planned to happen during the whole year until the end of 2021. And that's it. Thank you for your attention, and I hope this information was helpful.